So section 3, measures of variation. So section 2 is about measures of center. That's mean, median, mode, then mid-range, all that stuff was in there with that. So measures of variation, measures of center are getting us, to the middle of the data. Variation, what that means is how far are we going away from the middle? How much is each data point away from the middle? That's what variation is going to get us to. So standard deviation is where we're going to hang out most of the time today, is standard deviation, talking about that. But it's understanding and interpreting the standard deviation is what we're after here. Not so much calculating. We're going to talk about the formula for that you can use a hand formula to get standard deviation. But we got a graphic calculator that can find standard deviation for us too. It uses the same formula. It just does it all instead of having to do that. Especially with a large set, it's tough to do. It just takes forever. It's not hard math. It's easy math. It's just a lot of the same operation over and over. So there's a lot of places to make mistakes. So part 1. There's a couple of different parts of this section. Range. That's a measure of variation. This is the same range you've known since you were in elementary school. Biggest value minus the smallest value. That's the range. Nothing's changed about that. Okay. Range. When we talk about all these different things, we talked about mean the last couple of days. With mean, if you make a 0 on a test, it can be very detrimental to your average, right? So an outlier is going to affect mean. It's also it affects your range as well quite a bit. Okay, so anytime you have extreme values, your measures of center can be affected quite a bit, especially mean. But then your range could also be affected, which your mid-range would be affected a lot too. So if you've got some outliers, okay, so that range, it's sensitive. Okay. Round off rule, measure of variation. Is it a calculated value? Is it? Okay, so what's the rule for calculating on center? One more decimal place. So the same thing here, because it's a calculated value. Okay. Measures of variations are going to be calculated values. So you're going to go one more decimal place than what your data has. Range is a calculated value. One more decimal place than what your data has. Only the final answer. If there's an extra calculation in the middle, like we talk about standard deviation, there's a calculation before the end. Don't round that middle step. Always just round the final answer. Don't round in the middle of the problem. That's good. For math class, that's the way you want to do things. In science class, they had this whole thing about significant figures and all that crazy stuff. It's weird, but be careful of that. So one more than the decimal place, but only the last answer. The final answer is the only one you're going to round. The rest of them don't round at all. Peyton had an interesting thing come up on his calculator when he was putting some of the data in. It was a longer number, and he was putting in like 27,000, something 0.5. But the calculator kept showing it as rounded up 1. But if you go to that data point in the table, it actually still had the decimal place that he put in there. It may change the way it looks in that table, but it's still using the value you typed in. So don't worry about that so much. But that's a kind of a default thing that the calculator does when you put things in list. It kind of tries to make it fit on the page, which is I'm like, well, just make the thing wider. That's harder than things. Standard deviation. This is where we're hanging our hat for most of the day today. Set of sample values is denoted by lowercase s. Okay. Sample standard deviation is a lowercase s. That's pretty easy to remember. Okay. It's a measure of how much data values deviate away from the mean. Okay. So what the standard deviation does is it figures out how much each data point goes away from the mean. Is it above it, below it, that sort of thing. Okay, standard deviation is how far each data point is from the mean. Deviate. Lowercase s. So when we look at our one variable stats on our calculator, the lowercase s, if we're dealing with a sample. Lowercase s, if we're dealing with a sample. Dealing with a population is different. We'll get to that in a minute. Lowercase s, how far each data point deviates from the mean. That's an important definition, knowing what standard deviation does. A lot of things we're going to build upon. Standard deviation kind of helps us to get there as far as some of the things we use when we get into hypothesis testing. Some of our values are based off of standard deviation, so we've got to be able to, you got to know what it means so we can kind of get an idea where it's going. Here is a formula for sample standard deviation. It's an A formula. Not the formula, but A formula. There's more than one. Okay. The square root of the summation of each data point. So X here represents the data points, remember. X bar is the what? The mean of the what? Sample. It's a sample mean. So each data point minus the mean, and then square that. And then you're going to add all those numbers up. And then they're dividing by n minus 1. What's n? Number of values in our data, in our sample. Okay? They're using n minus 1 instead of just plain old n, because it's a better estimator than n. It is nice of it. It really working for it. Excel will do similar things to it. It does that for you, which is wonderful. Because you would have to do you'd have to do that subtraction for every single data point that you got. So if you had one of those tables that's like in the appendix of your book that you had to look back through, whichever one and two, that'd be miserable to have to do that. So niceness of the calculator can help us with that. Here is a shortcut formula for that. Which it involves taking the sum of the squares of each data point and then the sum of all the data points and then squaring that value. And then you got to multiply the sum of the squares by n, subtract, and then you're dividing by n times n minus 1. It says shortcut formula. The formula's got more stuff in it, but it's actually less operations if you had to do it by hand. It doesn't get far away from the same number until way on down the decimal point line. It's very, 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 very close. Like we're talking 4, 5, 6 decimal places before it starts changing. So it's a shortcut formula for that. It really, either way, guys, I'm not going to have you try to do this by hand anyway. Okay, just showing these formulas exist. If your calculator dies, those formulas exist. You can actually calculate standard deviation by hand. Okay? All right. Fun stuff. We got that formula, got that other formula. All right, here's the important things about standard deviation that we've got to know. It's a measure of variation for all values from the mean. So it's all, it's not the average of those things, but it's for all the values. The value of S is positive. It's never negative. It says usually positive. That's just like, okay, I'm usually this tall. I mean, that sort of thing. It's never negative. Okay? The standard deviation is never going to be negative. Okay? So it's always positive. It says usually. It's always. It can increase dramatically with the inclusion of one or more outliers. That goes back to the variation stuff. If we've got extreme values, then variation is extremely sensitive to that. So standard deviation is going to be sensitive to that too, because you look at, if you've got a really, really high number and you do the mean, let's say the mean is like 12 and you've got a number that's like 65, that's really far away from it, right? So when you compare that to the mean, they're, you know, how many, 52 or 53 apart? That's a big way. And then when you got to square that and then take the square root of that answer, it really can change your standard deviation a lot. So extreme values can cause some problems with that. It really can change your standard deviation by having those outliers in there. No, it's sensitive. We talked about that already. Standard deviation has the same units as the original data points. That's important. Okay, units are important when you're talking about data. When you're trying to share things with people and information, if you say something about standard deviation, you just put a number. You don't put units on that. Then sometimes that can throw red flags as to, okay, they really don't know what they're doing because they didn't say that that's, you know, it deviates 45 questions, you know, or 4 questions from the mean or something like that. 4 correct answers from the mean. It's got a unit. Okay, standard deviation has the same unit as the original data values. Those are some important properties of standard deviation. All right, let's do a problem. Use either formula to find the standard deviation of these numbers. Okay, we got 4 of them. We can do that by hand if we wanted to. First thing you got to find in order to find standard deviation is what? The mean. If I add all those up, 10, 14, 2, 4, 6, 8, 9, 94, divided by 4, 2, 3, 23 and a half. If you put them into a table on your calculator, stat, edit, gotta delete these out of here. So I don't have to. I technically could have went to list 3 and done it, but didn't. 22, 22, 26, 24. And then I go to stat, calc, one variable stats. And do I have a frequency list here? No, so make sure you get rid of that. If you use that, if you should have used that on the test. 23 and a half the mean, okay? Standard deviation, S of X, 1.91. How are they figuring that out? Well, you're using that formula from, that formula right there. So you take each data point and subtract the mean. So you'd have 22 minus 23.5. And then you'd have the same thing again, 22 minus 23.5. And then 26 minus 23.5. So you do all those things. Get those values. Negative 1.5 twice. Negative 1.5. 2.5. And then that's 0.5. And then you square each of those values and then add them up. And then divide by 3. And then take the square root of that answer. That's a lot of operations if you had to do this by hand. Okay, so we don't have to do that by hand. There's all those values. 1.91. Go to our calculator. 1.914, all that stuff. That's wonderful. We got it. Okay. Here's a range rule of thumb. This is an important thing here. That the vast majority of your data, something like 95%, that's vast majority, right? 5% losing that's not a big deal. Vast majority of the sample values lie within 2 standard deviations of the mean. That means the mean is here in the middle, and then here's one standard deviation, here's the second standard deviation. But it could go the other direction. So this is your mean. This is the mean plus 1s. This is the mean plus 2s. This is the mean minus 1s. This is the mean minus 2s. That the 95% or better, your data is going to fall within that range. Okay. Usual values, okay, are what we're talking about when we say within 2 standard deviations. And that's what we're going to call those, usual values. Okay. They're not too extreme. They're fitting within that. We can find rough estimates of those minimum and maximum usual values, sample values, using these little formulas. Okay? The mean minus 2 standard deviations. So whatever you find for the standard deviation, you take the mean minus 2 times that number. That's going to be your minimum usual value. Your maximum usual value is going to be the mean plus 2 times whatever you find for the standard deviation. Those are how you determine if a value is usual or not extreme. Or better yet, you're testing if a number is an outlier. Is basically what you do. We're going to look at an example of that in a second. Okay? So those are little formulas for minimum usual value and maximum usual value. Make sure you know those. Mean minus 2 times s, mean plus 2 times s. Minimum is on the minus side, maximum is on the plus side. All right. We can roughly estimate the standard deviation. It's not going to be exactly right, but we can take the range and divide it by 4, and that'll give us a rough estimate of what the standard deviation is going to be for a sample. Okay. Remember, range is maximum minus minimum from our data. Okay, maximum minus minimum from our data. So if I ask you to estimate the standard deviation, this is how you're going to do that. Range divided by 4. Okay, for estimating the standard deviation. All right. Here's our example. It's going to kind of put this into work. Okay. We've got a 40 chocolate chip counts for the Chips Ahoy cookies. The mean, so what we did was took 40 cookies and counted how many chocolate chips for each cookie. And the mean is 24 chips, and the standard deviation is 2.6 chips. We don't have all of the data, we just got this information. We don't have those counts. We just got this information. We want to know what are the usual values, minimum and maximum for number of chips. Okay? If the mean is 24 and the standard deviation is 2.6, what is the minimum usual value for that? So to find the minimum usual, we're taking 24 minus 2 times that standard deviation. And that's going to get us a minimum usual value. For the maximum usual, taking 24 plus 2 times 2.6. 5.2, so 24 minus 5.2 would be 18.8. It's a maximum usual. 29.2. Okay, so what that tells us is anything below 18 is an outlier. That's not usually what happens. Right? Anything above 29, outlier. That's usually not what happens. Right? So we answer this question: would a cookie with 30 chocolate chips be unusual? Is that outside of the 29?
Yeah.
Yeah, that's an unusual cookie. That's 30 chocolate chips. 29, technically not unusual. 30, yes, unusual. If you're a chocolate chips ahoy chocolate chip cookie lover, you'll count the chips every time you pick one up. I would, not just eat. So there's that happening. So we know that 30 chocolate chips in a cookie is an unusual number based on the information we were given, that the mean was 24 and the standard deviation was 2.6. 95% of our data should have fallen in between there, in between 2 standard deviations below, 18.8, and 2 standard deviations above, 29.2. 95% of the cookies you see are going to have that happen. The other 5% are going to be split between the ones that have less than 18 and the ones that have more than 29. That's kind of how that's what we're looking at here. Different samples. It's a good practice to compare 2 sample standard deviations when the sample means are the same. If you've got 2 different samples, like say, Grace, you counted some chocolate chip cookies in your pack, and then I went and did another sample and picked some and counted them. But our mean, when we did all our data, your mean was somewhere around 24. But when I did mine was somewhere around 15. Those 2 samples are very different because the means are not close together. So it's hard to compare her standard deviation with what mine would be because the means are not very close. Okay? And standard deviation is a calculation based on what value? The mean. So if the means aren't close to standard deviations, they're hard to compare. And that's what it's saying here. 2 different samples, it's hard to compare them when the means are very different. If the means are about the same, if hers is 24, mine's like 23.2, that's pretty close. So our data, we could compare the standard deviations and probably be, they should be close too, probably. Okay. When comparing the variation in samples with very different means, it's better to use a coefficient of variation, which we'll talk about in a little bit. Okay, we'll get the actual definition of that. Okay. We'll get that. All right. Population standard deviation. What's different about this formula compared to the other? It's got mu in it. Mu is the what? Mean of a population. What's capital N? Number of values in the population. Okay. Remember on the standard deviation for a sample, we used n minus 1 in the bottom, not n. So we took 1 away from that. It's different. They're a different formula. Your calculator, if you've got a population, you've got all the data. It uses this formula to find that sigma x on when you do one variable stats. That sigma x is this formula. Similar, but it's populations, not samples. Bless you. All right. Bless you. Variance. Variance is related to standard deviation. It's the square of the standard deviation. To find the standard deviation, you have to take square root at the end. Well, we undo that. We have what's called the variance of that standard deviation. Sample variance, S squared, is how we note that. And then sigma squared for population variance. Talk about variance. It's the same formulas. You're just taking that value from your calculator and squaring it. If it's a sample, you're squaring the S. If it's a population, you're squaring the sigma of your one variable stats on the calculator. At what point would we round when we do that? What point would we round? Just going back to what we talked about just a few minutes ago. After you square. Don't round before you square. Okay. So when you look at your calculator, you got this value here. You've got to have all those decimals, all those numbers after that. Okay. What you can do if you need to square that, if I can remember how to get there, is hit the VARS button. A lot of people say VARS. It really stands for variables. And number 5 is statistics. And we can grab that S of X or SX. That's the standard deviation for a sample. And we can do that. If I hit enter right here, that's that same number from my one variable stats. I remember seeing that. If I want to square that, I would hit squared. And there's my variance, sample variance for that. So you can get that number without having to type it all in just by hitting VARS, go to number 5 for statistics, and then pick up whichever one you need. If you needed to use the mean to do something, it's number 2. If you needed to use the sample size, it's number, all of those things are there. If you needed to use any of those values, you can scroll on down through there and you see all of those things it gets from one variable stats. There's some summations that it'll do, some equation things from when you're doing regression lines and things. You can get some of those values. There are some test values. We'll get to that later in the year. We'll get to some of the using some of those. And these are some points on like from a graph that you can use those. So that menu, the variables menu, is nice. We'll use the number 5 there a lot. Okay, so just be aware of that. It will use the last one variable statistics that you ran. Okay, is the one that it stores in there. Aaron?
So it's after you square where you start to round.
Don't round. Yeah. So for our data set here, that 3.6 repeating would round to what as the variance? 3.7, because it came from this data set right here, and it had 0 decimal places, so we need 1 decimal place. 3.7 is what we can go for there. Great. Okay, so just some kind of business type things that we need there. All right. Sample standard deviation, sample variance. There's that notation. Sample variance is an unbiased estimator of population variance. Okay, unbiased estimators. Those are important things. So know that word, unbiased estimator, which means that the sample variance tends to get close to the population variance instead of underestimating or overestimating that. The part of the reason that it gets closer is because of the n-1 on the bottom of the formula. If we used n for the sample size and not n-1, it would actually underestimate it. Why the n-1 is there. Folks that come up with this stuff, they did enough of them and found out, hey, if I put n-1 here, it gets a lot closer to the population variance than they don't. So sample variance is a good unbiased estimator of population variance. Unbiased estimator. Those are going to be coming up some. All right, that gets us through part one of section 3. You got time to get through part 2. Part 2 is much shorter. Okay. Here's what I was just talking about. By dividing by the n-1, it gets it closer to the population variance. A lot of that, I think, is due to trial and error. They tried using n for that variance on samples, and come to find out it was underestimating the population variance every time. So that, well, if we take 1, how close is to get it? And it got much closer every time for that. So I think that was a kind of the idea when they were developing some of this stuff to decide which way to do it. Is that n-1 works more. Gets it closer to the population. And we want our sample, things from our sample, we're trying to make some sort of generalization about a population when we have a sample, right? That's the whole idea of statistics. Is you take a small sample and make some sort of assumption or general statement about the population. So we want anything we're calculating, we want it to end up being as close to the population's size, whatever that value is for the population. We want our sample to be close to that as possible without some sort of error. So n-1 using that in samples and not in that. This is an important rule, the empirical rule, or the 68, 95, 99.7 rule. If you'll memorize those numbers instead of the name empirical, it'll help you. I call it the empirical rule, and I'll probably still refer to it as the empirical rule, but if you'll remember those numbers, it will help. 68, 95, 99.7. 68, 95, 99.7. Okay? It's for distributions that are approximately bell-shaped. Bell-shaped means it's probably what kind of distribution? Normal. And we like for things to be a normal distribution. Okay? Some things that apply. 68% of all the values are within 1 standard deviation of the mean. So if we're dealing with a bell curve, %, and I'm let's try to do it. That's better. 68% of our data falls within 1 standard deviation. So that's between here. 68% of the data. 95% of the data is within 2 standard deviations. We've already talked about that. About those usual numbers, minimum usual, maximum usual numbers. That was the 2 standard deviation stuff. That's the stuff we did here. That's that same 95%. 3 standard deviations of the mean get 99.7% of the data in a normal looking distribution. Okay? 68% within 1 standard deviation, 95% within 2 standard deviations, 99.7% of the data falls within 3 standard deviations of the mean. 68, 95, 97, or 99.7 rule, empirical rule. Okay. I think the next is a nice picture of that. Huh? Here's a nice picture of that. I've shared this PowerPoint with you so you'll be able to look at it closer and have that good picture to look at. But 68%, 34% on each side. Then you add another 13.5% on each side there. That gets you your 95%. You add about 2.14% for the other part to get the 99.7, and that leaves 0.13% on each side for anything outside of 3 standard deviations. Okay, so everything falls around that mean. Most of your stuff is within 2 standard deviations. 99.7% is within 3 standard deviations. Now here's Chebyshev. That's how you say that. Chebyshev, his theorem. The proportion of any set of data lying within k number of standard deviations of the mean is always at least 1 minus 1 divided by k squared, where k is a positive number greater than 1. Okay? The proportion of any set of data lying within k number of standard deviations, okay, is always at least 1 minus 1 divided by k squared. That's Chebyshev's theorem, or formula that goes with that. Press the button. There we go. For k equaling 2, at least 3/4, because 1 minus 1 over 2 squared would be 1 minus 1/4. 4 over 4 minus 1 over 4 is 3 over 4. Okay? Three-fourths for k equaling 3, 89% of all the values fall within 3 standard deviations of the. This is a little different normal distribution. This doesn't necessarily have to be a normal distribution for Chebyshev's theorem. Okay? He was making this statement for any distribution. Okay? That's one of the main differences here in the numbers. K equals 4, you can do, be 15 out of 16. 15/16 of the data will fall within 4 standard deviations. That was his theorem. I bet he had a hard time learning to write his name, Chebyshev. Even though it had the same letters in it, it just seems hard to spell. Here's an example of that. If we got that IQ score, they keep bringing that one up. Have a mean of 100 and standard deviation of 15. What can we conclude from Chebyshev's theorem? Well, at least 75% of those IQ scores are within 2 standard deviations. We know that based on 1 minus 1 over k squared, if k is 2. We know that within 3 standard deviations, we're getting 8 over 9, or 8.9% of the IQ scores are between 55 and 145. Where did 55 and 145 come from? Yeah, you take the mean minus 3 standard deviations. We know the standard deviation is 15, so 3 times 15 is 45, and we subtract that from the mean, and that gets to 55. 145 is 100 plus 45. Same way with the 70 and the 30. It's 2 standard deviations, minus 30 and plus 30. All right. Variations. We mentioned this earlier. If the means are not the same, or not relatively close, then comparing those with a coefficient of variation is good. There's a couple little formulas here for dealing with the sample. It's sample variation, or sample standard deviation divided by mean of the sample times 100%. So you turn it into a percentage. Population, sigma divided by mu, so the population standard deviation divided by the mean, and turn it into a percent. Coefficient of variation is always expressed as a percent, and it compared. What it does is it gives us this ratio of standard deviation to the mean, which is more comparable when the means are not the same for 2 different samples or 2 different populations. We can compare those coefficients of variation to see if the data vary very much just based on that. So it's relative to the mean for that particular sample or population. That's what that makes it. So coefficient of variations, know that formula for that. And it's always a percent. That's the last thing in this section. Pretty easy stuff. if you want to go ahead and start on problems for that, page 106, 1 through 46. We get into a little bit more stuff where you got to actually do some math out of it. So, look at those things and